Hello, everyone. Hello. Nice to see you. Are you enjoying TriSwift conference? Yeah? Okay. 3 more sessions to go, and I will be the first one. I mean, the last first one, okay? And it's an honor to be a speaker of this TriSwift conference, talking to great developers here from all over the world. I want to say thank you to all of you coming to here in Japan. My name is Yasuhiro Inami, and today I would like to talk about one of the most fantastic technique in functional programming. It's called Parser Combinator. By the way, I come from the company called Line Corporation, and it is a messenger app company located in Shibuya, very next to here. It's actually next building. So I come from next building, actually. So this one, right, Line Corporation, okay? So anyway, let's get started. Parser Combinator. Has anyone ever heard of this one before? Please raise your hand if you have ever heard one. Okay, quite a few people know, but well, probably most of us doesn't know. But don't worry, I will briefly go through what parser and combinator means. Here, first is parser. As most of you probably know, parser is an analyzer that takes a string as an input and creates this kind of syntax called syntax tree. Parser basically consists of 2 parts. First part, the lexer, takes a raw string and converts it into small chunks called tokens. And then, for the second part, the syntactic analyzer takes that tokens and creates this kind of tree. Let's see this a bit more. When we do parsing, there are mainly 2 approaches. One is called bottom-up parsing, and the other is called top-down parsing. For example, in here, there's a string in the bottom, say a equal b plus c times 2 semicolon d equal 1. How do we parse this? In what order? In bottom-up parsing, we take a closer look at the bottom tree first. As we read each text, at some point, we can convince that we can construct the end tree, like this part. And as we keep reading the text, we can construct the tree bigger. And lastly, we reach the top. So the parsing starts from bottom to top, like this order in the image. This is called bottom-up parsing. On the other hand, there's also a top-down parsing. What it does is, you read the text, partial text, and at some point, a bit earlier than bottom-up parsing, the top-down parser starts to predict what kind of tree node should come at the top. And it keeps guessing down to the bottom, like this order. This is called top-down parsing. And here are some algorithms in parsing. And I won't talk deeply here. But let me just tell you that today's topic, the Parser Combinator, is about the recursive descent parser in the middle here. And it's actually a top-down parser. By the way, if you have ever read the Apple Swift code before, in the parsing, the code is in live parse. And actually, it also uses the same technique in C++ with non-DSL imperative way. So we are now understanding about what parser is. How about combinator? Well, in this slide, I put many symbols like SK, I stuff. And actually, this is a kind of field called combinatory logic. And it's also an interesting topic to discuss. But I don't have much time today, so I won't go further here for now. For now, just please think that they are just a function or closures in Swift. And they can be combined together to form a more interesting characteristics. And finally, Parser Combinator. In short, Parser Combinator is just a higher order function that combines multiple parsers together to form a one big parser, like the image on the right. You can see that there are two parsers, the inside parsers, and they are collaborating each other. And it looks like one big parser are working. This is just a parser combinator. So how do we implement this in our first language, Swift, right? We prepare a struct, a simple struct called parser. Uses the generic type A here. And it's actually a container of the closure. As you can see, the red parse. And it takes a string as input. And in this case, the output is the tuple. The tuple consists of result part and the remaining input part. Because the parsing sometimes fails, I use the optional here. This kind of structure is so-called state monad. And it combines the maybe monad or maybe optional monad together. And from here is a monad showtime. So please be prepared if you don't know, but it's not so difficult, so just relax. To get started, we first prepare applicative pure and alternative empty like this. The pure is just instantiating the parser, and it passes a return closure. And inside that closure, you return the tuple, which means this parser is always successful with returning the value A. And it doesn't actually consume the input, but I will talk about it later, maybe. And for the empty, the nil is returned. That means this parser is always fails. Let's move on. Bind or flat map operator. It can be written like this. First, you receive the input. You see the closure, and the input is passed as an argument. And you parse that with the given parser P. And if that parsing succeeds, you get a tuple of it, and you extract the result part. And you apply F. And that F result will be a second parser. And you use that parser to apply for the remaining input. In this case, it's input 2. Otherwise, if the first parser fails on the first place, you just return nil. That means the whole parser fails because the first parsing fails. And once you got this flat map operator, you can immediately get the functor map, functor F map like this. In Swift, it's map, and this is a bit special case, but we don't use the dollar sign. Instead, we use the caret sign because we can't use the dollar sign for the custom operator. It's pretty common in the Swift community, right? Next, let's see alternative choice operator. So in this one, you have a parser P and Q are given. And what this does is you try parser P first. And if that parsing succeeds, then finish. You just return that tuple. If it fails, you try Q instead in the bottom like this. So it's just like P or Q. Quite easy, right? And I would like to mention also 3 important applicative sequential operations like this one. Looks weird, but please relax. And, and the first one is called app. And it's just a function application for monadic structure. And the second one is a sequence action. And it looks like an arrow pointing to the left. At least it looks like to me. It's look like the left side, right? So what this does is it tries parser P then Q. It uses both, but only use the left side of the output of P. And it means it discards the output of Q, not using this, only using this one. And the last operator is just the opposite. We try parser P then Q. It's same as before, but only use the output of Q, not P. Okay? So this is it for the custom operator. And you all now know about monad. So I'm sure you are now all feeling monadic now. Okay? So let me introduce some more parsers. Here's satisfy parser I implemented. And what this does is it basically examines the input. You decompose it using the uncons function. It's the head and tail part is you get those, and you examine the head part with the predicate. And if that predicate succeeds, you get the decomposed tuple. Otherwise, the whole parser fails. This satisfy parser is quite fundamental parser that you should remember for today. And such as you can create like any parser that can parse any one character, or digit parser that can only parse the numeric number, numeric character, or some specific character such as that is declared in char parser like this. It's all readable, simple. Next, here's a bit complex parser called string parser, and I don't talk this too much because it looks weird. And in short, this is just parsing the specific string. Otherwise, it just fails. And here are some important parsers called many and many one. What they do is the parser P is given, and they just use that parser P many times. That's it. But to explain more, the first many parser uses the parser P from 0 occurrence to many occurrences, and that it never fails. While the many one parser must be able to parse at least one occurrence of P. Otherwise, it fails. Please notice that they are mutually recursive. And here are simpler skipping parsers called skip many and skip many one. It looks just like same as previous many and many one. But please notice that this part, the result part, it's now an empty void, empty tuple. Which means a meaningless output. So this seems like useless parser at first glance, but actually it's more efficient, more good performance than many and many one. And we can implement like very important parser called skip spaces. As you can see, the implementation, it's just skip many space. It's very common when we want to parse things. We want to skip spaces, right? But we don't actually care whether it's tab or line feed or whatever. And last but not least, let's add symbol and natural parsers. Please just take a look at this one, a bit like 10 seconds maybe. Do you see any pattern here? You might be noticed that there's a middle parser in the middle that is sandwiched by skip spaces parser with an monadic, the applicative arrow-like operators, like pointing like this direction, this way. So what this does is, it first skips the head white space, and then applies the middle parser, and lastly, skips the tail space, but only use the output of the middle parser. It doesn't care about the spaces, only cares about the string part, in the above case. So it's like a hamburger. 2 breads on the side, a delicious meat, beef, cheese, vegetables in the middle. And we all care about this part, right? Right? Okay, so it's just like a hamburger. And for the symbol parser, the delicious part is a string parser. While for natural parser, the delicious part is many one digit, which actually converts the result part from string to integer. It's mapping, actually. So we have just talked about many burgers, the parsers. And you just saw the small codes each, actually. Only like 3 lines of almost, maybe sometimes 1 line. And now we can play a simple math. Here, it looks a bit hard to maybe see it, but let's use the plus sign, multiple sign, what is it? Parentheses, and natural numbers to make a simple calculator. The arithmetic expression grammar will be like this. This is called Backus-Naur form, and it's pretty common when you do some parsing stuff. And in Swift, our first language, we implement something like this. Actually, I used the light recursion here, but just think you can write in like almost in one line. Actually, it's last 3 or maybe some more lines, but a bit weird, but it's still simple, right? And here goes a calculation. Say 12 plus 3, super long space, times 4 plus 5 is expected to be equal to 65. And it works according to this slide. So yes, we made it. We made such a calculator that even 1-year-old boy can solve. Okay? Yeah, you might be now asking, oh, I'm not interested in 1-year-old math. I want to do something more cool stuff. So you want to do more, right? No? I'm just wondering. At least I want to do it myself for myself. And here's actually good news. I have one more thing for this. For those who wants to enjoy parsing more, I developed a small library, which is very fun for this talk. And please let me introduce Triphasic. The name, I think it's obvious, so I don't say it. So Triphasic, I developed it, and it's a monadic Parser Combinator just for this TriSwift conference, nowhere else. It's inspired by Haskell, and especially Parsec and JSON libraries. It supports not only 1-year-old math, but also CSV, XML, and JSON. Technically, it can parse LLK grammars with arbitrary K lookaheads and with backtracking by default. Which means, as well as this library not using the do, try, catch in Swift 2 stuff, this Triphasic doesn't actually try anything. Doesn't use any try keywords. But please hold on. I want all of you here to try it because this is TriSwift conference. Okay? But please wait. I just announced this library, but actually this library is not open source yet. But I will right after this conference. So why? Because I want all of you to hear to listen, not reading the code while I'm talking. So please be patient and stay a while and listen. Here are some basic functions of Triphasic. You have already seen about half of it, maybe. And there are still more half important functions too, such as sep by, it's actually separated by, not a good Cocoa naming convention, but forgive me. And like count, chain L, like skip while, and so forth. And they are also fundamental functions too. So please check them out as well. Now let's see how this Triphasic works with JSON. In Triphasic, the enum JSON is already built in, like this data type, enum, very common, basic time. And let's say we have a JSON string like this example. How do we parse? All we need is just call parse JSON. And you immediately get the JSON enum tree. Simple and easy. In this process, I didn't use any NS-JSON serialization, or no, any object is not involved in this process. It's all written in pure Swift. But actually, we are not actually interested in this kind of structure. because this is just an intermediate representation. And what we want is not that intermediate stuff. We want our custom model to be mapped to it. So we need JSON decoding and encoding features, right? Which we all have. And Swift has like 28, 30s of libraries for doing so. Fortunately, Triphasic offers the 31st JSON decoding and encoding library. So let's see the JSON decoding example first. Let's prepare the struct model like this, which we just saw the JSON string example, and we just want to map to this one. In the bottom, I added the let dummy. I didn't. The JSON string doesn't have this field, but actually I did it for purpose. And how do we map? I mean, before that, actually, only one thing you have to do is implement the conform to the from JSON protocol, like this. In here, you implement a static bank from JSON, and you use the helper method called from JSON object. And inside that, you see some kind of weird stuff like this. And actually, this is pretty famous writing called applicative style writing. And if you have ever tried the famous JSON library called Argo, thought about Argo, this Triphasic also uses the same technique. And just call function decode, and you get the mapped result. Simple. And for JSON encoding, all you have to do is just conform to JSON protocol, like this, and use the helper function JSON object, and pass the array of the key value pairs, like this one. And just call function encode, and you immediately get back the JSON string. It's very simple. So I haven't open sourced yet, though, but let me just summarize what this library is. So you just see the example of JSON. It supports JSON, and also it does do the parsing the CSV and XML too. So please check it out. And it's very simple, readable, and easy to create your own parser. So please take a try. And I also will attach the Xcode playground for this one, so you can play around with it. But let me point out some caveats here. One is that actually this is not good, does not have a good performance yet compared to NSJSON serialization. And second, there's some limitation in using the from JSON and to JSON protocols. I mean, the mapping. It actually, any library, I mean, like Argo and other great libraries, such as Ikesho's decode library, maybe, they have a limitation just because Swift is currently limited. Swift 2 doesn't support one of the key features called higher kinded types. And because of that, actually, from JSON to JSON doesn't have, is kind of limited. But I'm pretty sure that in Swift 3, we'll solve these problems. Why? Because Swift 3 is now open source. I mean, Swift is now open source. It is evolving every day. And we have already great community just right here, right? So I'm positive to improvement on Swift, supporting the higher kinded type. And eventually, this library is going to get better. But I also want all of you to check out my library and improve the code base too. So this is it for my talk. Thank you very much for listening. I'll hear any questions. Thank you.
Really, really awesome. Really cool stuff.
Yeah.
I actually have two questions. You can pick which one you want to answer.
Okay.
So the first one is there any support for errors? So if the parsing fails, can you maybe annotate your parser combinators to say, hey, if this part fails, maybe I want to throw this kind of error here? And the second question is, how did you do the to JSON? Do you have like a pretty printer combinator library as well?
No, not pretty. Let me just answer the second question first. There's no pretty printed JSON stuff yet. I think I need to implement that. For just now, it's just a one-line JSON string. And the second one, actually, the error reporting is important, but actually, I didn't implement it because the performance is already bad at this point. So I need to improve that first, and then go to the error reporting, better error reporting. So sorry about that. Okay. Okay. Thank you very much, everyone. Have a nice last 2 seconds. Thank you.